Okay. So here, in order to explain Lenz's law, first what is taken? A coil. Coil, that means in the form of a solenoid. What is a solenoid? Number of turns of insulated copper wire wounded in the form of a spring. That is a solenoid. And what is connected to the ends of the wire? Galvanometer. What is the use of galvanometer? To detect the presence of current. And then a magnet also, you can see here. This is north pole and south pole of the magnet. When north pole of the magnet is moved towards the coil, when north pole of the magnet is moved, I think maybe due to net. This never happened before. Okay. North pole of the magnet is moved towards the coil. What happened? The flux, these are the field lines. Field lines pass from north pole and they end in south pole. Inside, the field lines are south to north. Outside, the field line direction is north to south. So only two field lines are shown there, and many field lines are present there. Here, when the magnet is moved towards the coil, the flux means field lines passing normal to this area. The magnetic flux linked with the coil is increasing. When the magnet is moved towards the coil, the flux linked with the coil increases. When the magnet is taken away from the coil, flux linked with the coil decreases. So first we are discussing about the motion of the north pole of the magnet towards the coil. When it is moved towards the coil, flux linked with the coil increases. So whenever there is a change in magnetic flux, an EMF will be induced in the coil. That is Faraday's law. According to Faraday's law, an EMF will be induced in it. That how will you detect the presence of EMF? Whenever there is an EMF, current will flow through the coil, and that will be detected in the galvanometer. So when the north pole is moved towards the coil, we can see a deflection in the galvanometer, which shows that a current is induced in the coil. So here, when the north pole is moved towards the coil, what is happening? The flux increases. There is a change in flux. So, in order to induce an EMF in a coil, there must be a change in flux. Simply flux is not enough. See, if both are kept stationary there, magnet and coil, both are kept stationary there, no EMF will be induced. Galvanometer will not show any reading. But when we move either the coil towards the magnet or the magnet towards the coil, there is a relative motion between the magnet and the coil. There is a change in magnetic flux linked with the coil, and therefore an EMF will be induced in the galvanometer. Or current will be, EMF will be induced in the coil, and that can be detected in the galvanometer. Clear? So here, you see how it can, according to Lenz's rule, the polarity of the induced EMF always opposes the cause which is producing it. What is the meaning of that? The polarity of the induced EMF, which pole will be developed by inducing, here an EMF is induced and a current will flow, and when current flow in anti-clockwise direction, that part will be north pole, and if the current is flowing clockwise direction, that will be south pole. That we have studied earlier. So here, when north pole is moved towards the coil, to oppose that motion, a current is induced, that and current is induced in such a way that a north pole is developed. The north pole only can repel another north pole. So the pole developed here, when current is flowing through this solenoid, one end becomes south pole, other end becomes north pole, depending upon the nature of the flow of current. If the current is flowing in anti-clockwise direction, that part appears as north pole. If the current is flowing in the clockwise direction, that part appears as south pole. So near to the magnet side, near to the facing the magnet side, which pole will be developed? The pole developed is in such a way that it opposes the flux. That means change in flux. Opposes the change in flux. How it can opposes the change in flux? Here, movement of the north pole towards the coil, that is the reason for the change in flux. Movement of the north pole of the coil towards north pole of the magnet towards the coil is the cause of inducing that current, inducing that EMF. That cause is opposed. What is the cause of the induced EMF? North pole of the magnet is moved towards the coil. That is the cause. Change in flux is produced due to that motion. That motion is to be opposed. How? By inducing a current in the coil. So, in which direction current should flow? To oppose a north pole. Anti-clockwise direction current should flow. Then only that pole developed at the top end of the coil. The pole developed at the top end of the coil will be north pole, which will oppose the motion of the north pole towards the coil. Clear? So, what pole will be developed when north pole is moved towards the coil? Which pole develop on the top surface of the coil? North pole is developed. So, such a way the current is induced in the coil. It always opposes the cause which is producing it. So, the EMF is produced by the change in flux. It opposes the change in flux. How it can opposes the change in flux? By producing a pole there. And when that changes into a magnet, when current flows through the coil, that changes into a magnet. So, near to the north pole of the magnet, and north pole is induced. That means current is induced in such a way to form a north pole there. So, anti-clockwise direction current flows here. That is the meaning. So, what is Lenz's rule? According to Lenz's rule, the polarity of the induced EMF is such a way to oppose the cause which is producing it. Such a way to oppose the cause which is producing it. What is producing the EMF? That cause is opposed by inducing current in it. Thereby, a pole will be developed to oppose that north pole, anti-clockwise direction current. Then I will ask another question. If the north pole is taken, Ashley, outside. Okay. Listen. So, if next case, if north pole is taken away, then I will ask question. You have to tell the answer. When north pole is taken away from the coil, flux linked with the coil decreases. When magnet is taken away, number of field lines linking with the coil will be less, decreases. Number of that means magnetic flux linked with the coil decreases when the magnet is moved away. North pole of the magnet is moved away from the coil, flux linked with the coil decreases, and then also EMF will be induced. So, whether it is increase in flux or decrease in flux, that is a change in flux. Change in flux is to be opposed. How it opposes? By inducing an EMF in itself, in that coil. So, when the north pole is taken away from the coil, which pole will be developed to oppose that motion? North pole is taken away. That motion, how the coil can oppose? In which direction the current flow? Can you tell? In which direction the current flow? Bhadra?
Clockwise direction.
Clockwise direction, correct. Give a clap to her, that's correct answer. Clockwise direction current flow, and the south pole will be developed here, and the galvanometer shows deflection in the opposite direction. When north pole is moved towards the coil, suppose the deflection is towards right, and the north pole is taken away from the coil, then the deflection will be towards left. Opposite deflection you can see. Similar way you can see south pole is moved towards the coil, a south pole will be developed. Like that, same way. So, north and south pole deflection also will be opposite. So, I think you understood it. So, Whenever there is a change in magnetic flux, an EMF is induced in the coil. And the current flows. Whenever there is an EMF is induced in the coil, current flows, and we can detect the presence of current in the galvanometer. And if they are kept stationary, no EMF will be induced. That means there should be a relative motion between the coil and the magnet. Either you can move the magnet towards the coil, or you can move the coil towards the magnet. That is, there should be a relative motion between the coil and the magnet. Then only the flux linked with the coil changes. Whenever there is a change in magnetic flux, EMF will be induced and current flows through the coil, and it is detected with the help of galvanometer. So that is this experiment that is explained here. The next page. So Lenz's law and energy conservation. You can see Lenz's law also obeys energy conservation. What is energy conservation? Energy can neither be created nor be destroyed. It can only be transformed from one form to another. That is what we have studied. So Lenz's law, you see, a coil and a magnet is there. How electrical energy is produced there? According to energy conservation, we cannot create energy, but actually here current is induced, electrical energy is produced there, no? How it is possible? How it obey energy conservation? You see, in order to move the magnet towards the coil, work is to be done. So that work done is converted into electrical energy. You see, mechanical work done in moving the magnet with respect to the coil is changed into electrical energy. So thus energy is being transformed. Mechanical work done is converted into electrical energy. When we do not move the magnet, work done is zero. Therefore, induced current is also zero. Hence, Lenz's law obey the principle of conservation. Usually, along with the Lenz's law, this question also asked. How explain it is in accordance with the energy conservation. So you can see we are not actually creating any energy, not at all creating energy. Only transformation is taking place. The work done by us, we are moving the magnet towards the coil. Work done by us, mechanical work done by us is converted into electrical energy. One form of energy is converted into other form. That is in accordance with the energy conservation. Okay. So Lenz's rule gives what? Very important. What does the Lenz's rule give us? Lenz's rule gives us the direction of induced current. Lenz's law gives us the direction of induced current. And one more rule gives us the direction of induced current. That is Fleming's right hand rule. So both rules can be used, Lenz's rule or Fleming's right hand rule. Remember, it is right hand rule that gives us the direction of induced current. Then let us state what is the right hand rule, Fleming's right hand rule. So for that you have to take your right hand, and thumb, you can see thumb represents the direction of motion of the conductor. Here the conductor is moving, and forefinger represents field. These two are the known quantities. Then what will be the direction of induced current? That is given by the central finger. Always remember, thumb represents motion. M, in order to remember, you can use that word M is there to represent the motion of the conductor. Forefinger, FF. Forefinger, field. Remember, forefinger, field. Similarly, central finger, C, current. Central finger, CC. Central finger, current. Remember, don't forget. Forefinger, field. Central finger, current. Thumb represents motion. Which are the known quantities here? Motion of the conductor and forefinger. That means magnetic field. These two are the known quantities. Motion of the conductor and magnetic field. Then induced direction of the induced current is given by central finger. That is the statement. If we stretch the first finger, central finger and thumb of our right hand in mutually perpendicular direction such that first finger points along the direction of the field and thumb is along the direction of motion of the conductor, then the central finger would give the direction of induced current. So that is the Fleming's right hand rule. All of you study very well. The Lenz's rule, what is Lenz's rule, what is Faraday's laws, what is right hand rule, all everything is to be studied well. Okay, motional EMF, very important derivation in electromagnetic induction. Motional EMF, motional. Motional means due to the motion of the conductor, an EMF is induced. Motion of the conductor in a magnetic field induces an EMF in it. That is motional EMF. So EMF induced across the ends of a conductor due to its motion in magnetic field is called motional EMF. So when a conductor is moved in a magnetic field, an EMF is induced. So due to the motion of the conductor in a magnetic field is inducing the EMF in the conductor. That's why it is called motional EMF. So an experiment is explained here to find the expression for motional EMF. So induced EMF at the ends of a conductor moving perpendicular to the magnetic field. So here you can see a Induce mark. You can see Induce marks. They are equally spaced Induce marks. Equally spaced Induce mark represent what? Equally spaced Induce mark represent magnetic field perpendicular to the plane and into the perpendicular. So Induce mark represent magnetic field perpendicular to the plane and inwards. Okay. Then what you can where is PQ? PQRS. That is a rectangular frame. You can see a rectangular shaped frame. And PQ is a conductor kept on that frame. PQ. That is movable one. PQ can be moved in or out. When it is moved inwards, the area enclosed by the loop decreases. When the PQ conductor is moved away towards the right, area enclosed by the loop increases. So in this particular case, when the conductor PQ is moved inwards with a velocity v, velocity how will you calculate? Distance by time. If the dx distance is moved, dx by dt in a time dt, dx by dt will give the velocity with which the conductor is moved. So what all things you can see? A perpendicular magnetic field, direction of magnetic field is perpendicular to the plane and inwards. And another thing, a rectangular coil is kept in the plane. Rectangular coil is kept in the plane. And you can see a conductor which can be moved. PQ is a conductor which can be moved over that frame. And the conductor is moved towards left. The area enclosed by that loop will be less. And the conductor is moved towards right, the area within enclosed by the loop will be more. In the magnetic field, this is kept in a magnetic, perpendicular magnetic field. Okay. So here EMF induced, we are going to calculate the EMF induced. So EMF equal to minus d phi by dt, equal to minus d phi by dt. EMF induced equal to minus d phi by dt. Phi, how will you calculate? Phi, magnetic flux, BA cos theta, flux equal to BA cos theta. So, how will you calculate BA cos theta? A is the area, B is the magnitude of the magnetic field. Cos theta, what is theta here? What is theta here? Theta is the angle between B and A. B and A. A is the area vector. Area vector means normal drawn to the area. So, magnetic field is perpendicular to the plane inwards and area vector is also normal to the plane. So what is the angle between B and A? What is the angle between B and A? B means perpendicular. You keep your forefinger perpendicular to that figure rectangle. Keep your forefinger perpendicular, touching on it, perpendicular to that. Area vector is also perpendicular to that. So what is the angle between B and A? Ismail, what is the angle between B and A? Ismail? 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 Why not answering? Then I will call Fatima. Fatima?
Teacher, 0 അല്ലേ?
Yes, 0. Correct answer. Angle between B and A is 0. Okay, correct. You are thinking? Okay. Anyway, answer is correct. Because magnetic field is perpendicular to the plane. Normal is drawn to that area. Both are making an angle 0 degree. Okay. So, BA cos theta, cos 0 is 1. So, B into A will give the flux. Flux equal to B into A. Appa cos theta 0, cos 0 I 1 I. Appa B into A madi flux kandupidikka. Area angane kandupidikkum. Area is length into breadth. L into X. Length into breadth. So, the conductor PQ is moved inwards with a velocity V. And area equal to L into X. So, flux equal to, you can see flux equal to B into L into X. L into X is the area enclosed by the loop PQRS. So, flux equal to B into A, B into L into X. According to Faraday's law, E equal to minus d phi by dt minus d by dt of BL into X. B is constant, L is length also not varying, only dx by dt. X is changing. When the conductor is moved inwards, this distance, that is changing with time. Dx by dt is changing. So, minus BL into dx by dt. Dx by dt is velocity. Dx by dt is velocity. You see, here minus BL into dx by dt is taken. Next step, you see minus sign is not there because we take minus dx by dt is the velocity which is decreasing direction. Area decreases. At that time, when we take minus dx by dt is the velocity towards left. If it is area is increasing, we take dx by dt as positive. Here, minus dx by dt is taken as V, or dx by dt will be minus V. Okay. Negative direction, that's why. Decreasing direction. Conductor is moved in such a way to decrease the area. So, we got the expression dx by dt is V, and we got the expression for the EMF E is equal to BLV. Very, very important expression. When a conductor is moved in a perpendicular magnetic field, EMF induced in the conductor is equal to BLV, where L is the length of the conductor, V is the velocity with which it is moved, and B is the magnetic field induction at that position, which is perpendicular magnetic field. Perpendicular magnetic field. EMF induced, small letter E, EMF induced. So, I think you understood that. If any doubt, you can call me. Next to another important, this is also important for doing problems, application questions also come based on this equation. So, induced EMF at the ends of a conducting rod rotating in a magnetic field. The earlier case was not rotating, that is just moved in a perpendicular magnetic field. This case, EMF is induced at the ends of a conducting rod rotating in a magnetic field. So, the conductor is rotating here. You can see a conductor here of length L. OP is a conductor. Conductor means what? Material which allow the current to flow through. Copper, it can be copper, aluminum, gold, silver, like that. Metals are good conductors. So, such a material. OP is a conductor of length L. And it is rotated. In which magnetic field? Perpendicular magnetic field. Into mark represent magnetic field perpendicular to the plane and inwards, as we have seen last case. Magnetic field is perpendicular and the conductor is rotated. So, consider a conductor of length L rotates with an angular velocity omega in a perpendicular uniform magnetic field B. By Faraday's law, the induced EMF at the ends of the conducting rod E equal to minus d phi by dt. Minus sign only shows the direction of the induced EMF. So minus is not taken here. D by dt of B into A, flux equal to B into A, perpendicular magnetic field. So we need only to consider B and B into A. B is not varying, B into dA by dt. As the rod is rotated, area enclosed by that loop closed part will be varying, so that we have to differentiate B into dA by dt. So we got the EMF, and the A you have to substitute it here, different cases. So let theta be the angle between OP and OQ. Then the area swept by the rod A equal to area OPQ. So initially it is at this position OP, and it rotated through an angle theta. Anti-clockwise direction it is rotated. Motion is a rod is rotated in anti-clockwise direction. So when it is rotated and when it takes this position OQ, so initially OP position rotated anti-clockwise direction, and the new position is OQ. Then what is the area enclosed by that OPQ? That we have to find out. So total circumference is equal to pi r square, and for that the total angle traced by the radius vector will be 2 pi radian. So for this total circumference pi L square, the angle subtended at center by this radius, that will be radius means by this rod, that will be pi r square by 2 pi. Pi r square by 2 pi, and for the small angle theta, the area will be pi L square by 2 pi into theta. For unit angle, the area will be pi L square by 2 pi, and for an angle theta, it will be pi L square by 2 pi into theta. And the pi cancel, we get L square theta by 2, area enclosed. So induced EMF equal to a B into d by dt of area. In the place of area, we substitute this value when it rotates through an angle, d by dt of L square theta by 2. So half into BL square into d theta by dt. What is d theta by dt? That is angular velocity. So EMF equal to half into BL square omega. So when a rod is rotated in a perpendicular magnetic field, the EMF induced will be half BL square omega. So two derivations we have studied. When a conductor is moved in a perpendicular magnetic field, EMF induced E equal to BLV. When a conductor is rotated in a perpendicular magnetic field, the EMF induced will be half BL square omega. Omega is the angular velocity, L is the length of the rod. Only 5 minutes more. Okay. Then current produced in a loop. Yes, current produced in a loop. You can, same case, a rectangular loop, and you can see a conductor PQ, which can be moved in or out. That means it can, when it is moved towards left, area enclosed by the loop decreases. When it is moved towards the right, area enclosed by the loop increases. Let the conductor PQ is moved towards left with a velocity v in uniform magnetic field B as shown in figure. Let R be the resistance of the movable arm PQ. This arm, that resistance is R, let us take, that is the R. While other sides QR, RS, ST has negligible resistance. We consider only resistance of this arm. This is taken as R. So current will be EMF by resistance, BLV by R. Current induced will be small letter I equal to BLV, EMF induced by resistance. According to Ohm's law, EMF by resistance, that will give the current. The force acting on the movable arm PQ is F equal to BIL sin theta, force that we have studied, force acting on a conductor. current carrying conductor in a magnetic field equal to BIL sin theta. And what is the angle between B and current element IL? Angle between that will be 90 degree. Magnetic field and this length of the conductor. Length of the conductor, not area, length. So that will be 90 degree. So BIL sin 90 is 1. So B into I already calculated BLV by R into L. So F is equal to B square L square V by R. This force is acting outward and hence to move the arm with a constant velocity, it should be pulled with the constant force. So this force is acting outward, you know. How will you be knowing the direction of the force using left hand rule? Direction of force you can find using left hand rule. So current flow direction, suppose in that direction is shown. See, using Fleming's right hand rule, you can find out the direction of the induced current. Conductor is moved towards left. Conductor is moved towards left. And then 90 field is perpendicular to the plane. All of you take your left hand and find out the direction of force acting on it. Direction of force is given by Fleming's left hand rule. Understand? So if current is flowing downwards and the conductor is moved towards left, you can hold your finger in that manner. So the force is acting outward and hence to move the arm with a constant velocity, it should be pulled with a constant force. So it will experience a force always in the outward direction. It will experience a force in the outward direction. You hold your left hand, central finger current, and the motion of the conductor is towards left. Motion, thumb represents motion of the conductor. And then field, forefinger represents field. Forefinger is perpendicular to the plane and inwards. And current, you can see the direction of current is downwards. Thumb will be showing right. You please hold your left hand and find the direction of force acting on the conductor. Current is downwards, it is marked there. Actually, we have to find out current direction with the Fleming's right hand rule. Current is downwards and downwards. Central finger represents that. Forefinger represents field. Your forefinger you have to hold perpendicular to the screen, and into that nailed part is into that, touching the screen. Then thumb gives the direction of force. Yes, thumb gives the direction of